All right. Welcome to Cybernetic Snacks, a speaker series featuring leading voices in the cybernetics conversation. We're currently exploring the past, present, and future of cybernetics. Today, we're going to do something a little different from the rest of the series and speak with someone whose work is informed by and inspired by cybernetics, rather than being squarely centered in the field of cybernetics itself. In the next 20 to 30 minutes, our speaker will cover the answer to 4 questions regarding the thoughts on their work in relation to cybernetics, its past, present, and future. Following the session, you'll be able to find a recording plus a snack pack of resources related to the talk to take home and look at on our website. To keep it focused and on time, there won't be time for audience questions, and you'll see we won't answer the chat to limit distractions. Straight after the talk, our speaker will join our PhD students for their ratio club for Q&A. For everyone else, we encourage you to create opportunities in your own communities to continue the conversation. So before I introduce our speaker today, I would like to acknowledge the traditional custodians of the lands on which we are speaking with you today, the Ngunnawal and Ngambri people, and pay our respects to elders past and present. Our Cybernetic Snacks guest today is a creative whose work is inspired and informed by cybernetics. Australian-based artist Jonathan McCabe follows a unique code-based process to create vibrant generative animations infused with pattern formations and geometric shapes found in the natural world. For pieces like his VCINet one currently on display at the immersive 8K lobby screen inside the US Bank Tower in LA, McCabe implements algorithms first developed by Alan Turing and finds inspiration in scientific theory and biological development. So let's get started. So Jonathan, thanks for joining us today. What draws you to cybernetics, even if it's not your primary field?
Well, thank you, Jess. I'm so pleased to be able to talk about my work and its relation to cybernetics. Yes, cybernetics, the ideas of cybernetics, I feel have really permeated culture, and in a way they're inescapable. The idea of systems and the way they come to their goal-seeking behavior, I think that comes from cybernetics, which, as I understand it, was really going off in the 1940s and 1950s and 1960s. But the idea of feedback, I think it's become very mainstream now of guidance in systems, and I'm drawn to it. I'm very interested in spontaneous pattern formation, and there are theories of well, we see it in the natural world, and I've been very interested in the theories of pattern formation and simulating them on the computer and using them experimentally. And I've ended up calling it art, and thinking of myself as an artist. Though I think I originally approached it from a sort of thinking I was a scientist, a scientific kind of approach, and trying to model systems. But now I'm using it in an artistic kind of way. And my work is it's in the field of generative art, which is part of systems art, which did come out of the cybernetics movement. And in generative art, the artist sets up a system which produces the output, and it's a bit anti-art in some ways. If you look at, say, painting, it's more direct, the control of the output. And in generative art, it's indirect. But I like to think of it in a similar way. Photography is indirect, and there is other art, which is, I think when photography came out, people said, is it art? It's not really art. And now people go, of course it's art. So I think it takes quite a while. And there's other kinds of generative art, and I might share my little PowerPoint. Here we go.
Sounds good.
Cool. Start. Oh, yes. So about generative art. Goodness. Okay. The artist makes the system, and then the system produces the art. So it could be sound or images or video, or it could be 3D, all kinds of things. It can be all kinds of output. It doesn't have to be software and computers, though most of it is at now that computers are the machine of the age. And it's a subfield of cybernetics art. But I think this is how I got into generative art, which was Spirograph, which I had when I was little, and it's a drawing machine. So there's a whole tradition of drawing machines of various sorts. And the Spirograph, it's got these cogs, little wheels. You put a pen in and rotate it. And depending on the ratios, you get all kinds of patterns. But I think it's really a kind of generative art. There's other kinds of generative art. There's this is David Bowen in Hungary. This is a drawing machine using the wind and leaves and charcoal. So I'd say that. So I'm just like to make the point that generative art is it's more than just computer art. The particular kind of generative art I've been very interested in has been Turing patterns. Yes, so let me see. Sorry, I just jumped out of that and jumped into something else.
No, that's okay. I suppose that this is probably where it leads into my second question for you,
Yes.
Jonathan,
Yes.
about looking to the past, about particular tools and ideas and theories or people from cybernetics that might shape
Yes.
your thinking.
That's right. So Alan Turing was an English mathematician, and he was very important in the development of computers, digital computers. And of course, he helped crack the Enigma code in World War II. He's famous for that. But near the end of his life, in 1953, he published a paper about pattern formation in living things. He had a theory of how stripes develop. I'm sorry, I'm having trouble navigating because I can't get to the toolbar now. Whoops, so sorry about that.
It's all right.
How's this? Oh, goodness. Okay, sorry. So, yes, Alan Turing posited that, for example, stripes on animals, say zebra stripes, can be formed by a process of diffusion of signaling molecules, where you have an activator which acts at a short range and say leads to the pigment cells becoming dark, and you have an inhibitor that acts at long range, which inhibits the cells from becoming dark. And so these two kinds of feedback, a positive feedback for local. Oh, sorry, I'll just stop my sharing. Oh goodness, I'll just stop here. Sorry. Oh, sorry. The two kinds of feedback lead to stable patterns. And so this is the idea of cybernetics, of positive feedback and negative feedback in a system, guiding it to a conclusion. And I came to Turing patterns. I was very interested in cellular automata, which is also comes from cybernetics, comes from John von Neumann and Stanislaw Ulam. I came through it by Stephen Wolfram, who will not mention cybernetics at all, but clearly his ideas have come from. He gets in trouble for not citing anybody else besides himself. But I was very interested in cellular automata, but I did find I was getting stripes and spots in my cellular automata, which I'd heard of Turing patterns. So I looked into that and found that they'd sort of accidentally started producing Turing patterns.
Do you have examples of those?
I do. So I'll just, yeah. I have some examples of Turing patterns I've made myself. There's this idea that I believe the earliest I've found is John von Neumann of dividing space and time into tiny little squares, which are like pixels today. I think it seems like it's a very straightforward idea, but you can sort of see where it starts being used in simulation. And here we have each pixel can sort of know about what the pixels around it are doing, and they're communicating by having a short range activator, which is it's encouraging the other pixels to become black or white, depending on their neighbors, and the long range inhibitor, which is telling the ones further away to become the opposite. And time is divided up into steps, and it starts off just being gray random pixels, and then you get stripes in this case. And after 10,000 time steps, you end up with very smooth, regular pattern. And this is a stable pattern. Then I tried adding these together. So I've got a basic process that produces some kind of pattern. And I tried adding them at different scales. And I think I had seen, say, leopard spots and goanna spots. They seem to have some structure at multiple scales, not just spots. And so I thought I'd just add them together. And you can add them together in different ways. And this gives you scope to select and to try to produce different patterns. Then I decided to add some symmetry and add them at different scales. So this is an idea from fractals of variation at different scales. So I've sort of fractalized Turing patterns and added some symmetry. So this is a good thing about an artist. You don't really have to justify what you're doing. You just call it art.
Try things out.
It's art. And then this is a combination of having multiple Turing patterns and the different scales idea. So this is what I ended up with in 2010. And more recently, let me see. More recently, I've been doing this on my Instagram. This is interacting Turing patterns of different scales. And they end up giving you these structures. I've just got a few different colorways here. You can color them different ways.
Are there any rules that you apply when you're working with the colors, or do you just do what feels good?
Oh, and in this case, the computer just picked the colors. And then I selected from a set that it had produced. Well, that's very common with generative artists. They actually get the machine to produce a huge number of outputs, and then so it's, I guess it's sort of like found object. You just pick out of that and find things. That can be. Oh well, sometimes you might find something really good. Often you wouldn't, and that's where other methods like genetic algorithms from John Holland, who is in the field of cybernetics, he sort of gave a mathematical description of genetic recombination and how and it's from the idea of recombination in plants and animals of their genes, how that's actually searching a space of possibility, and he formalized that. And I was very taken with that idea. I think I read his book, which he published in 75. I read it in 96, and I went, oh, this is great. And the good thing about that is if you're doing selection and recombination, you can select for the parts of things, and then the parts can be recombined. Whereas if you select right at the end for the whole thing, it's very unlikely that you'll get a good combination. And you can imagine that life on Earth couldn't be where it is now without the recombination in populations where there can be selection on lots of the sort of component attributes of the organisms can happen in parallel. You couldn't get evolution like that in a single line if you were just selecting by living or dying. You need recombination of population to make it an effective search.
Yeah, wonderful. And so sort of on what you're discussing there actually leads into my next question, which is cybernetics today is often how we about how we shape systems and are shaped by them. So, where have you seen cybernetic thinking applied in your field or beyond to change something in the world?
Oh, I'd like to talk about a project I was involved with, where cybernetic thinking is part of the project, and it's probably got the biggest public effect of what I've done, my work. And it's an installation at Stanford University, um, which at the Bass Biology building. It's it'll be about 6 years ago now. It's the part of it is this large screen, which is over 2 stories at the Bass Biology building. And here we can see 6 interacting Turing patterns. Now, each one of them would just become stripes by itself, but they're pushing and pulling on each other. And this has no stable equilibrium. You can see stripe patterns, but they immediately sort of lead to their own destruction and movement. Um, so I think this shows the cybernetic principle of well, in a way, there's a stable pattern, but it's moving, but it's parts which are seeking a certain state, and feedback is directing them. And then this is a composite system uh, where you get more complicated behavior. And here's the user interface where people get to design, or well, they get to control the strength of the interactions. Down the bottom right hand, there's sliders where you have 6 string patterns. You can change the size of them, the color, and how they
Mm.
interact with each other. And here we see someone perturbing the system, but it's actually sort of resisting him and going back to stable stripes.
Mm. And I'm just curious, actually, as well. The colors in his jacket seem similar to the colors on the screen. Is that just coincidence, or is the
Oh, okay.
pattern
So
reacting some way?
this is the iridescence. I think this has all been staged very heavily. And here is one of the presets that I found, I think, and put them in. So you can just take a preset. There's a few of them. And someone's jacket matches that so exactly. It's
Mm,
uncanny, but I think that's all completely staged, I'm afraid.
no worries.
Um, but, um, and oh, yes, and so here's a mainly a black and white one, but you can see it's being perturbed. Where the fingers go, it's actually being destroyed, but it's recreating itself. Yeah.
Mm. And how did you feel like people reacted to that work where they could perturb a system?
Oh, the people. I had reports that people were very excited by it and being able to interact with it.
Mm.
Um,
Mm.
and yes, and having a lot of fun with it. That's what they told
Mm.
me. Um,
Was there anything that was unexpected about the interactions?
um, Let me see. Uh, yes, I don't think so. It is very constrained in a way. It does
Mm.
spots and stripes, and that's what it
Mm.
does.
Yeah.
Um, there and the parameter space is so large that it's probably very hard to understand it. And something with say 2 interacting Turing patterns would be easier to understand.
Oh, interesting.
Um, so probably it should have had the facility to be simpler to as an educational tool. It might just be very complicated
Mm. Mm.
and a bit messy.
Yeah. And so, finally, if you had the chance to shape the future of cybernetics, even as an outsider or occasional collaborator, what's one thing you would change, challenge, or reimagine?
Oh, I think it's very interesting, these theories. In a way, cybernetics claims to explain just about everything, and in a way, it does. Everything is a system, and interactions are of this form of positive and negative feedback. And I feel it was very popular a while ago, and then it sort of became mentioned much less. I think this has happened with some other theories. There's, for example, chaos theory. Uh, might have heard of it, and it's hardly mentioned now. It featured in Jurassic Park. Um, I I think these theories, when they have something surprising to say, and they're in opposition to the mainstream theory of how the world works, they have their time and they're mentioned to explain lots of phenomenon, and then people feel that they're overused and there's a big pushback. And I think in chaos theory, the idea that a system can be completely deterministic and yet unpredictable, that was against the mainstream thinking.
Mm.
That people did used to think that if you could completely describe a system and simulate it, you could exactly predict how it would go. And it came up in simulations of the weather that you can have a description of a system, but it can be very sensitive to the initial conditions of the simulation. And any slight change in those conditions leads to larger and larger change over time. And now I think that this is a mainstream idea that a system can have divergent paths, but it was surprising at the time. And so chaos theory, that was, I think, the main idea of it. Because before that, people did say that if you could simulate the universe, you could run it exactly and know what would happen in the future, things like that. And now we know, of course, you can't possibly do that. The tiniest little thing leads to larger and larger consequences. And I think earlier, before that, there was catastrophe theory, which comes from cybernetics as well. And I think the main idea in that is that a system which has smooth parameter changes can actually show jumps in behavior. And people would have thought that things like stock market crashes or all kinds of, which in a way is catastrophe, come from external influence on a system. They look for an external influence. But catastrophe theory showed mathematically that smoothly changing internal parameters can lead to instability and a change in the system. And apparently it was used in economics to explain a lot of things that economists couldn't explain. Because economists, they used to love to use just very simple relationships, demand and supply, which gives you one minima, and there's always one solution. And it turns out that in the real world, there's multiple solutions to what's actually going on. And they couldn't really explain stock market crashes. They had to talk about the irrationality of humans. But in catastrophe theory, it actually makes complete sense for rational actors to lead to these catastrophes. And it was used to explain all kinds of things. And then, and this was in the 70s, I think. And then there was a complete backlash against it, and people don't talk about catastrophe theory anymore. So I think that in a way, these theories have the seeds of their own destruction embedded in them. They start off with ideas which are surprising and have explanatory power, and then the ideas themselves become part of the mainstream, and people go, "Oh, that's just obvious." And so, in a way, cybernetics would be, you would know it was it had sort of won and been effective when people stopped talking about it, paradoxically.
Yeah. And I guess I'm just curious as well, like any, before we wrap up, any links that you might see between what you were just describing in terms of, an idea changing over time and your work changing over time?
Oh, yes, my work has it's sort of got stuck. Still doing things I was doing in 2010, which is and I feel it's due for a big change. I don't know what will happen. So I've been combining these simple systems and elaborating them, and I think my work's it's different from a lot of other work in the area in that I'm doing that with the compound systems.
Mm.
Oh, yep. Oh, and let me see. But I've taken that a certain away, and they've gotten so complicated that I can't possibly work out how to make them do what I want, and
Mm.
they're a mess. So
Oh,
I'm
it's
sort
very
of,
interesting. Like I think it seems sort of like that you can just keep perturbing the system until, you get sort of different kinds of results.
yes.
Well, thank you so much, Jonathan. I
Okay.
think that's all we have time for today. If anyone would like to know more about anything we've discussed today, you'll find some resources online when we make this recording live. I'd like to thank Jonathan McCabe. We've learned a lot about directness versus indirectness of an artist, about Turing patterns and about spaces of possibility. The experience isn't over for our speaker and the PhD students who are now off to have a more informal discussion about cybernetics and Jonathan's work. To the rest of you online, thank you for joining us and see you next time. We'll be encountering a very different perspective once again. Thank you.